containing 5 million tons of contained copper, the ore zone typically would have an extent of around about 1 square kilometre. So that's the size of the target you're trying to hit. And obviously, if that's buried under several meters, 100 meters of cover, then it's quite hard to put a drill hole into the ore zone itself. But of course, there's a wider zonation of sulfides around that, so disseminated pyrite and so on, that may extend the footprint to several square kilometres. And then if we go to the traditional alteration halo around a porphyry system, that may take you out to around 10 square kilometres. So we have a bigger footprint from traditional methods that allows us to potentially intersect part of the system with drilling, and then hopefully you can be guided in towards the centre from the mineral assemblages and things that you have there. But of course, you need multiple drill holes through the cover to understand where you are in the zonation. If you can use the green rocks, you have a much bigger target. The propylitic alteration may give you a footprint of around 50 square kilometres, so much bigger target. But if you get a sample through drilling into those green rocks, how can you use that to work out where the centre is? And that's what I'll show you. So back to our cartoon, imagine now it's eroded down, but the deposit hasn't been intersected by erosion, so it's still hiding beneath the surface within its own alteration envelope. So green rocks, large extent of green rocks at surface. What we can do is obviously we can take propylitic samples at the surface, there may be a bit of shallow drilling we can get some samples from. And then what we wanted to be trying to do is to use the information in these samples to tell us where the center of the system is. Different scenario where erosion has gone down into the ore body and then there's been a later cover over the top. And of course, this later cover won't necessarily contain any information telling us about what's underneath. So we need to go through that. We find some propylitic alteration in our drilling, and how can we use the information of these samples to tell us that there's an ore body over here? That's what we want to try and do. So the enabling technology here has been scanning electron microscopy combined with laser ablation ICP-MS analysis, so techniques that be familiar to many of you. This allows us to measure trace elements in minerals down to parts per billion, and that's a key feature of what we've been able to do. And we can also map the chemistry of the minerals using laser ablation. And these are just some images from chlorites from Bata Hijau that illustrate that we can measure a lot of trace elements in the structure of these minerals. Two key minerals, Epidote and Chlorite. I'll talk initially a little bit about Chlorite, and then I'll finish off with a bit on Epidote. So I don't have too much time to show you many examples, but I'll show you two examples of chlorite chemistry and how it can show you where the center of the system is in a propylitic sense. So this is the example from Bata Hijau. The white line here is showing you the open pit extent, so where the deposit sits. And these are gridded maps of chlorite chemistry for a range of elements. So you can see that the calcium in chlorite, cobalt and lithium and strontium are all low in the position of the deposit. So there's low contents of those elements in chlorite when you're close to the center of the system. Conversely, titanium shows a high, which we think is relating to the temperature of crystallization of the chlorite. So titanium substitution in biotite is thermally controlled. We think that's the same in the case of chlorite. So it's titanium elevations representing a thermal high related to the deposit. And the vanadium kind of shows a high shoulder. It's lowish in the center and then shows a sort of a high around the outside of the ore zone, basically. So these different elements in chlorite, trace elements at fairly low levels, are mapping out the sort of characteristics of temperature and chemical mobility that I've talked about already in terms of strontium and so on in the system. So some things are high proximal like titanium, some things are low proximal like strontium, lithium, cobalt. Second example from El Teniente. In this case, I'm plotting the titanium lithium ratio. So this enhances the signal basically by plotting or ratioing something that's high in the center to something that's being removed and is low in the center like lithium. And you can see here the titanium lithium map based on quite a lot of samples throughout this halo perfectly maps out the ore grade shell of the El Teniente deposit, even sort of mimicking its shape to some extent. And it also picks out these two satellite systems of La Huifa and Hoya Blanca towards the north. And these are older systems that predate El Teniente, but still have a presence, if you like, within the propylitic mineral chemistry. So you can see this beautiful gradient in this ratio that goes for several kilometers away from the El Teniente center. So based on a lot of samples, we've found that you can show that the gradients in chemistry of chlorite has a roughly exponential variation as you move away from the center. So looking at a ratio such as titanium strontium, a bit like titanium lithium that I just showed you, you can see that that ratio has an exponential decay as we move away from the center. There's a lot of scatter here, but you can fit a line, an exponential function through these sorts of relationships. Green one is Bata-Hijau, the red one is Alteniente. And that allows you to generate an equation that can be used to predict how far away a sample might be from a center in an unknown system. And how we can use that in exploration is just illustrated in this cartoon. This is map view. So imagine we've got a covered porphyry deposit under cover. We can take some samples on the surrounding exposed mountains, and some of those in red crosses may intersect propylitic alteration. There's maybe a sample down in a creek here, and then a shallow drill hole intersects some propylitic alteration. So we have a few samples with propylitic alteration in them. From the mineral chemistry, we can make predictions as to how far away each sample may be from the center, and hopefully those predictions would converge, and that then gives us the target that we can drill, hopefully representing the center of the hydrothermal system. Of course, these are spheres in reality in 3 dimensions, so it's a spherical kind of convergence, but that's a fairly simple geometric kind of calculation to work out where that convergence would be. So one example of how this was done, this was the discovery of resolution. I should emphasize this wasn't actually the real discovery of the resolution deposit in Arizona. It was already discovered. But this study was done as a blind test in one of the Amira projects. So the samples were analyzed blind. We didn't know where the deposit was, whether they were, which deposit it was or anything we were working on. We just measured the chemistry of the samples, and then we made the prediction as to where the center of the system might be. So these are drill hole samples that were used. There's the surface. So using these samples, the prediction was made about how far each one of those was away from the center using the chlorite chemistry, and that's what these circles are. So we're in a 2D cross section. So this is the circles that where the cross section is cutting through our prediction spheres, if you like, around each sample point. So each of the colors here is the prediction from a given sample point, and they all converge down here at the bottom of this cross section. It turns out the ore body is there, so it's sort of right. Prediction is right in the center, but just a bit too deep. And obviously, if you'd have drilled that prediction, you would have gone straight into the center of the ore body at resolution. So that was a blind test, but it showed that the technique could work for targeting deposits at depth undercover. Just finishing off with a couple of last slides on epidotes. So this is just illustrating a couple of the other things that we can do with the mineral chemistry. This one is showing you using heavy rare earth elements and arsenic and antimony and arsenic, how you can discriminate sort of regional background metamorphic type epidote from porphyry related epidote, which are the little small blue and red dots you can see here. So you can see the differences in composition that allow us to distinguish kind of background unrelated epidotes that we can get during metamorphism from porphyry related. And this also shows there's a difference between the epidote compositions that we get in copper gold systems from those that we get in sort of Cordilleran Andean type porphyry copper moly systems, which show a greater enrichment in elements like antimony and arsenic. And this slide is just showing you some of the more advanced statistical methods we can use to try and use the chemical information that's locked up in some of these minerals. So this is a linear discriminant projection analysis, classification of a whole load of epidote data based on samples that we've measured over the course of a number of the Amira projects. So using 11 elements, this diagram was generated to try and discriminate epidote that might be associated with high sulfidation systems, with porphyry systems, intermediate and low sulfidation systems, and also metamorphic background. So that's what this diagram is representing, a multivariate statistical method for classifying epidote chemical compositions. Now plotted on here are data from an area in the El Indio district in Chile, which is shown in map view over this side. And based on where the epidote data points plotted, we can classify the samples into what type of association we think the epidote was associated with. So the pink things here are where the samples effectively, the epidote has a high sulfidation type of signature. The red samples are ones where the epidote predominantly has a porphyry type of signature, and then the green and light sort of blue are where there's more of a background type of signature in the epidote chemistry. And you can then see how those plot in map view. and you find that there are specific clusters of samples that have either porphyry or porphyry high sulfidation transitional characteristics within the area. They're not randomly distributed. And these actually correspond to known prospects within the district where there are alteration centers and so on. So this is kind of illustrating how the epidote chlorite chemistry can potentially tell you where there may be porphyry related centers within a district. And this is the El Indio district, where there's a mixture of deep porphyry systems potentially and shallower high sulfidation. So we're in that kind of transitional environment. We're trying to navigate within that, and this shows how the epidote can help us in that regard. So just to wrap up, a couple of summary points. So propylitic alteration, we conclude, is generally metasomatic over quite large distances away from the porphyry centers, and involves significant minor and trace element mobility that we can record in elements in minerals such as epidote and chlorite. There's a huge amount of system information locked up in those hydrothermal minerals. So with the right technology and high quality analysis, we can extract that information, even parts per billion. Trace amounts of elements in some of these minerals is relevant and is systematic in terms of how it's distributed throughout these large hydrothermal systems. And certainly exploring the information using multivariate statistical and increasingly we're doing things like machine learning type approaches, we can reveal data relationships, which will hopefully help us in the challenge of discovery of major new porphyry copper deposits undercover. So I hope I haven't run over time too much. I tried to keep that within roughly the window, Marion and Jamie, but I'm happy to take questions now.
That was perfect. Thanks a lot, Jamie, for this really good overview. I think we can find all these papers from 2020 that you've cited in the new volume of Economic Geology. Jamie, it's a special volume, I guess.
Yeah, special issue last year in Green Rocks issue.
Yeah. Great. So yeah, while we are waiting for the question to arrive, I don't know if I miss it or so, but I was wondering how the surrounding lithologies are controlling the extent of the propylitic alteration.
Yeah, that's a good question. So the systems where you have volcanic host sequences, you generally, particularly intermediate or mafic host sequences, you generally get much more obvious and well-developed propylitic alteration, just because you have the precursor minerals that are favored for replacement. So the plagioclase and the amphibole and pyroxene and things that are relatively easily replaced by propylitic minerals. When you're in felsic host rock sequences, then the propylitic alteration is much less obvious. It doesn't mean that the extent is necessarily less, it's just much less extensive in the sort of the amount of the rock that gets replaced. So it's still there, but it's more disseminated and it's more fracture controlled. So it's sort of harder to recognize, if you like, but it is still there. So it's easier to work in environments where you've got mafic to intermediate volcanics, but you still have propylitic alteration assemblages in more felsic rocks as well. If you're in, we have worked in some sediment hosted porphyry environments, and they're more difficult, but again, you do get some propylitic alteration developed, but it is more restricted. So Bingham's a good example where there's a lot of quartzite surrounding the deposit, so you don't get much, sort of propylitic halo developed in the host sequence at all. But what you do see is where the latite dikes sort of extend out from the core of the system, you get propylitic alteration developed along those. So you do see it. It's just it is dependent to some extent on the host rock environment.
Okay. Great. Okay, we're receiving a couple of questions. Jamie, I don't know, maybe you want to start with the first one.
Yeah, sure. So the first question, I mean, we can ask you to unmute yourself if you want. So the first question is from Zira Deveci Aral. You can unmute yourself and ask your question if you want.
Hello, everyone. Thank you, Jamie. This is such a nice presentation. Thank you so much. I would like to ask you a question about the combination of this chlorite chemistry study with the zircon chemistry. Have you ever tried it, or what do you think about it? It can be applicable for the porphyry deposit exploration or fertility of the magmatic phases.
Yeah, absolutely. I mean, that's a great question. So we're actually doing more work at the moment on igneous accessory minerals like zircon, and you see in the image here on the screen, if you can still see it, that's an image of some of the zircons that we've been working on. So there are two parts to the porphyry sort of targeting story for us. One is to understand the igneous sequences, igneous centers, if you like, that could be associated with porphyry mineralization. So recognition of the magmas that are what we call fertile, so have the right characteristics to potentially produce a deposit. So that's the first thing, and that's useful in sort of more regional scale targeting for porphyry exploration. So you can recognize the belts of rocks or specific intrusions or intrusive complexes within those belts that may host porphyries, are favorable for hosting porphyries. So that'd be the first step. And then once you've identified those, then you can go into the alteration that may be present in those environments to then try and target where the center of the system is, and maybe even how well mineralized the system is based on the propylitic alteration as one example of one of the things that you could do to try and understand more about where the center of the system is once you've recognized the igneous potential. So there's two parts. The igneous part is an important, valuable tool in exploration as well.
Thank you so much.
Um,
Can I ask a very small question? It's a really quick one.
Okay,
in your slide, you showed the circles about talking about the Cook's paper in 2020. I'm really curious about the radius of that circles.
Right. So I mean, so they're in reality they're spheres in 3 dimensions. So what we're doing is we're taking a prediction of the distance from the sample, the estimated distance of that sample from what we think is the center, and creating a sphere of that radius around that sample point. And then if you have multiple sample points, you see where those spheres all intersect. And obviously in a cross-section view, they're just expressed as circles. But the radius of those circles, or the radius of those spheres, is the prediction based on, if I could maybe go back, it might be easier. Just go back. Based on the sort of gradients that we see in ratios as we move away from the center of a porphyry system. So on this slide, this ratio, titanium strontium, has this variation with distance away from Bata Hijau. And so we can create a relationship that expresses that distance as a function of the titanium strontium ratio. So the X is the distance, the titanium strontium ratio, and the chlorite is here. So we can use the chlorite measurement to make an estimate of how far away a sample is from the center. That's the X, that's the radius. Now you can see the slope is different for those two systems. And that's one of the issues with applying this sort of technique, is that the gradient of the relationship varies from one porphyry system to another. So around Bata Hijau, it's relatively steep and has less lateral extent, whereas around El Teniente, which is obviously a supergiant system, it has a lower slope and is broader, so extends further out. So you can't use one gradient that will apply to every system because it will differ according to which system you're working in. So obviously that's an unknown if you're in an exploration context, and that's where you can apply different equations. So you can apply different calibrations, if you like, to see where you get the best convergence of your predictions. And some of the companies have developed this in-house and have their own more sophisticated way of dealing with that unknown gradient, knowing that a gradient exists, but not knowing what the slope of it is. And there are ways that you can deal with that in a targeting sense. So hopefully that answers that question.
thanks,
Thank you
Jamie.
so much.
Okay, we have a lot of questions, especially about geochemistry, but just before getting into this question, we have a lot of questions talking about geophysics, so maybe we can tackle down this topic and come back to the geochemistry right after. Nick Arndt is asking, and this sums up a bit the rest of the question, which geophysical methods are most useful for finding porphyry deposits, and how can they complement the geochemical approaches you described?
Okay, yeah, that's a great question from Nick. So what I'm not suggesting is that this is a silver bullet is something you would use on its own. I think it is a very powerful approach, which can give a lot of extra information about what might be in a system undercover, particularly where you have a limited number of samples. But geophysics is obviously really important as well, especially for systems undercover, because it is the method. Geochemistry is indirect. We can make a prediction at depth using this approach, using geochemistry, which was something we didn't think we would be able to do. So these fingerprints are potentially telling us something about something that's at depth. But geophysics is a data type that is imaging, is actually reaching to those depths. So the combination of the two is extremely powerful, and particularly magnetic data would be very useful. So a lot of porphyry systems have a magnetic part to them because of the development of hydrothermal magnetite. So the combination of a magnetic anomaly with, if you like, a coincident green rock anomaly or a green rock target would be an extremely powerful result, which you would have a lot of confidence not only has the right geophysical characteristics, so there could be a system there, but also has the geochemical characteristics, which tells you that there is a system there. And if those two things converge, you've got the evidence of a hydrothermal system, not just, say, a magnetic intrusion, which doesn't have any hydrothermal activity associated with it. So the combination of the two is very powerful, especially magnetics. But IP also useful for detecting sulfide presence beneath the surface. So that would be another method that would be quite commonly used for things not under, maybe under a few hundred meters of cover. You can detect some of the sulfide dispersion or sulfide ore zone within a porphyry environment. And again, a coincident IP anomaly with a green rock anomaly and maybe with a strong fertility signal in the green rock mineral chemistry, which is something I haven't really talked about today, that would be, again, a really strong target. So the coincidence of geophysics with something like this sort of green rock prediction would be extremely powerful. It's a way of filtering the geophysical anomalies and focusing on the targets that are most likely to be mineralized. Basically, it helps you discriminate between different geophysical anomalies and focuses you on the right ones, perhaps.
Did you try to combine that on the blind model you've done?
So yeah, it hasn't really been done. I mean, it may well be that because a number of companies in the major companies are using these methods now and have been for a number of years. So it's very likely that they are combining these things, but we don't know what the details of those things are. All I can do is there was one case study I worked on where we did a green rock targeting in a site in Chile, and the prediction of the center from the green rocks alone was very strong, and then subsequently I found out that it converged or was perfectly coincident with a pre-existing induced polarization anomaly map that had been generated over the same area. So in that case, there was a perfect coincidence of the two, and it had been drilled, and there was a porphyry system that had been intersected at depth in that particular example. Again, it was a blind study, but it was a proof of concept that showed that the green rocks, especially if you just combined it with geophysics, could provide you with a target which actually was a real discovery at depth. And there's only, I think, a couple of drill holes in it. It was low grade, but it was a sort of it was still a success in the sense of it had detected a porphyry center at several hundred meters. I think it was about 600 meters below the surface.
Nice. Jamie, do you have the next question?
Yeah, I do. It's kind of there's two questions that are around I think the same thing. So I'll go with the second one. So can Juhani Ojala unmute yourself? You can ask your question if you would like.
Oh yes, yeah, Jamie. Just wondered because the chlorite obviously is pretty good on infrared in a sort of sphere near range. That did you do parallel with the mineral chemistry? Any spectroscopy?
Yeah, so we have done a bit of work on that, and we're continuing to do a bit of work on that. So we've done some. There was a paper published in Journal of Geochemical Exploration by Neil and myself and other colleagues on the Batu Hijau district. So in that case, what we did was use shortwave infrared spectroscopy of green rock samples. This was under lab conditions, so not in the field, but we were analyzing the same polished blocks that we'd used for the mineral chemistry analysis, and trying to extract spectra that basically in chlorite dominated samples that were reflecting the changes in the chlorite chemistry. So the spectral response is really only in responding to some of the major element substitutions and variation in the chlorite, but we do see that in the Badajoz and other porphyry systems as well. So like the magnesium iron ratio and silica aluminium as well. So there are some spectral variations that we showed in that paper that seem to be mapping out the major element changes in major element chemistry of chlorite. Obviously, that is harder to do where you've got, you know, a mixed mineralogy in the samples. There's overlap between the spectra for epidote and chlorite, for example. But if you've got chlorite dominated samples, we showed that you could recognize shifts in the spectra as you moved away from the center, basically. And one of the hopes was that you might be able to recognize some of those shifts in hyperspectral satellite data. So that's something we're just starting to think more about and do a bit of work on, is whether we can recognize some of these features in satellite remote sense data.
Yeah, I'll ask it. So basically, the first question he's asking, he's saying, firstly, what's controlling factors of trace elements in epidote and chlorite? So I think he's asking, you know, you've got different trace elements coming into the different minerals with respect to the porphyry. So what factors control their distribution?
Yeah, okay. Let me just quickly go back to, I didn't really dwell on this. There we go. Oops. So I guess one of the key things about these two minerals is that they have the potential in their structure to substitute a lot of elements, and we know that already. So we didn't have to do laser ablation to know that you can get substitution of a range of transition metals, for instance, into epidote. There are N-member epidotes that are lead epidote and so on, and manganese epidote. And the same is also true, less well known for chlorite. So there are N-member lithium chlorites and nickel chlorites and so on. So there was always potential for these elements to be fundamentally substituted into the structure of these minerals. We're not generally measuring kind of contamination or inclusions of other minerals. We try and avoid that. We're trying to just detect elements that are present within the mineral structure. And when we see the most systematic behavior for these elements in the dispersion in the sort of halo, it's generally for those elements where there is good evidence that they will fit into the lattice of those minerals. So some trace components like copper or bismuth, very often it might be micro inclusions of sulfide that we're detecting, not something that's in the lattice, and those things tend to be more erratic. In terms of what's controlling the substitution, we obviously have a lot less information on this because there's not that much experimental work and so on being done on this sort of low-level trace element incorporation. But what we think so far for chlorite, certainly, there's very good evidence that titanium is thermally substituted, as I mentioned. So there are chlorite thermometers, many chlorite thermometers already out there, which are related to the thermal dependence of the tetrahedral aluminium substitution in the chlorite. So if you calculate temperatures based on the tetrahedral aluminium substitution and compare that with the titanium content, you always get quite a good, strong positive correlation. So we're pretty confident that titanium, as is already known for biotite, is thermally controlled in its substitution. And in the propylitic halo, it's probably advantageous that chlorite is forming at the expense of minerals like biotite or amphibole that are quite titanium rich. So there's always excess titanium in the system. So the chlorite is buffered so that it will take as much titanium as it can into its structure as a function of the temperature at which it's crystallizing. So there's always excess titanium around in those kind of biotite chlorite or amphibole chlorite replacement reactions to allow the titanium to be buffered to the highest, so its maximum concentration as a function of the temperature, basically. So we're pretty confident that the titanium is a thermal indicator. Now that doesn't mean that means if you get a titanium anomaly in your chlorite in an area, you may be mapping out heat centers, but you may not be mapping out hydrothermal centers, and those two things can be different. So that's where the other elements like lithium and strontium we think are particularly important, because we think they're substituting as a function, more as a function of the availability of those elements in the fluid, and also the temperature, again, to some extent, or the pH of the fluids when the chlorite's crystallizing. So as I showed you from whole rock data, we know lithium and so on is strongly mobilized during the high temperature alteration out of the core of the system and is going into fluids, the propylitic fluids, and that further out, that lithium is then being incorporated into the crystallizing chlorite. So we don't know the exact control of that, but it's probably a combination of things like the decreasing temperature, the increasingly near neutral rock buffered pH of the fluid as it's migrating further out into the propylitic halo. Probably those two things are the most important two controls. So we're not 100% sure, but we think the lithium and other trace elements are representing the hydrothermal mobility of elements such as strontium and lithium as they're stripped from the core of the system and are transported outwards. And interestingly, what we see, and even in quite different minerals like chlorite and epidote, we see the same patterns with some of the trace elements. So if you have epidotes in a certain part of the halo that are enriched in zinc or vanadium or lithium or whatever it might be, you see the same pattern in the chlorite from that same domain. So although they're different minerals and the elements may be substituting into different parts of their structures, you tend to see the same enrichments or depletions of components in the same sort of spatial position. We've also seen this for magnetite as well. Magnetite can have the same enrichment, elevated zinc in the same spatial position as you see elevated zinc in chlorite or elevated zinc in epidote. So you do see this coincidence that seems to suggest that that element is reaching a point in the fluid where it's now starting to partition and precipitate into a whole range of different minerals that are then forming. So we don't have all the answers for sure. There's a lot of experimental work that would be good to do, but that's about as much as I can say for now.
No, that's a very thorough answer. It makes a lot of sense. So on the topic of strontium, I'm with respect to Bo, I have to move on to some other people. But Kay Jennings has a question on strontium, and since you touched on it, I think it's a good idea that they get to ask their question. So the question says, the question of strontium is intriguing. The flux is huge and surely must leave evidence of redeposition somewhere else. Any thoughts? Could we find subtle but significant indications even further out? That's what the question says.
Yeah, absolutely. So let me just quickly again illustrate with the slide here. So that's absolutely correct. So strontium is mobilized in a whole rock sense, we think, strongly out of the potassic core and the inner propylitic part of the halo. And that's what we think we're seeing in these sorts of maps. So we see a similar thing at El Teniente as well. There's a large area of strontium low in the chlorite, not just in the whole rock, but you see it in the chlorite. So the chlorite in the core of the system, and also in this case in Badajillo district, this low extends towards the west northwest, which is towards another prospect in this part of the area. So this is kind of like a higher alteration, temperature alteration domain where you've got more actinolite bearing propylitic alteration. That the chlorite is actually mapping out this low, which I think is reflecting the underlying broader magmatic intrusive complex upon which the porphyries are kind of sitting as apophyses. So there's a broad area of strontium depletion, net removal from the rocks, and as a result, a low precipitation of strontium in the chlorite that's forming in that environment, but it is being redistributed, and that's out onto the edge of the system where the strontium is actually then increasing and is then high. I haven't shown in this presentation some of the plots. They're in this paper in Journal of Geochemical Exploration, just to show how strontium increases with distance as you move away from the center. So it's not just a depletion in the center, it's also an addition on the edge. One of the things that's interesting with strontium and with some of the other elements is that it seems to increase out to the edge of the propylitic halo. And sometimes we haven't sampled far enough to know where that is. But then data from regional background samples suggests that strontium for those may be quite low. So there should be a cliff, if you like, where the strontium has reached its maximum sort of dispersion. And then beyond that, you just lose it completely because then you're just going into background. So it almost requires a wider scale sampling that we've done so far to try and identify these actual real edges of the propylitic halo where some of these elements are dispersed out more widely are actually then finally dropping off. So we think that the sort of things you're seeing here is actually some of the enrichment of strontium that's being moved out laterally. And it's not just chlorite. Chlorite picks it up, but strontium doesn't particularly like substituting in chlorite structure. So there'll probably be a lot of that strontium going into the calcite and zeolites and other minerals that are also forming in those more distal domains. And whereas as I said just now, where we have measured other minerals, we do tend to see the same patterns. So my guess is that if we had measured calcites out here, you'd find them to generally start to be more strontium enriched, kind of when they're more further out. But we see the pattern in chlorite, even though we're talking about in the core, maybe about 1 ppm strontium in the chlorite, and then out on the edges, we might be talking about 100 ppm strontium. So that's the sort of variation you're talking about for an element like strontium, about 2 orders of magnitude from the core in the chlorite to the edge. And the titanium is about the reverse. It goes from about 1,000 ppm maybe in the center down to about perhaps 10 ppm chlorite when you're several kilometers away. So if you ratio those two, which is what I showed you in some of those graphs, then you have a variation of that parameter, titanium strontium ratio, of up to about 4 orders of magnitude across the system from the core to the edge of the propylitic zone. So quite a big variation that, that's why you can map out these things quite effectively.
I have an anonymous question. I don't know which article he's talking about, but he says there is some case studies showing opposite trends in chloride chemistry, as we have seen El Teniente. What is your comment on this? And do you consider the lithological controls on mineral chemistry before attempting the mineral chemical vectors?
Yeah, so sort of 2 questions there. So if I take the protolith one first, so that most of the tests we've done for a primary bulk rock control on the chlorite chemistry show that most elements are not strongly influenced by protolith. There are some that are. So for example, the chromium content is strongly influenced by whether you have a mafic or particularly ultramafic host rock, which is fundamentally originally already enriched in chromium. So you get more chromium rich chlorites formed, for example. Vanadium is a little bit affected in a similar way, and also magnesium and an iron a little bit. So that they're more like varying by perhaps a factor of 2, if you like. If you went from a very felsic igneous rock to a very mafic one, you might get trends in the chlorite chemistry that are just reflecting that bulk rock variation, but only by up to a factor typically of about 2. Whereas the variations that we're talking about here that are significant are orders of magnitude. So although the protolith control exists, it's kind of like a blurring effect in the data. It's not completely undermining the patterns, and that kind of is inevitable from some of the areas we've studied with multiple host rocks. It doesn't matter if you plot all of the different lithologies together, you still see systematic patterns irrespective of that. Now obviously it's introducing some noise in there that may be confusing the pattern a little bit, but the underlying pattern still exists. So that's a protolith thing, that there's an effect. In terms of systems that show opposite behavior, I don't know exactly what opposite behavior you mean, but certainly with respect to how some of the major components behave, like magnesium and iron, there are differences from system to system. So at Bata Hijau, this example, magnesium is generally higher proximal, but probably shows a little bit of similar behavior to the vanadium, has sort of a shoulder around the edge of the system that is high, and then it decreases outwards. And iron is sort of similar to that, but slightly different. So generally more magnesium high proximal, but that's not always the case. So in some systems you see more iron-rich chlorite proximal. So there are differences certainly with respect to the iron magnesium behavior, and that may be partly reflecting the elevation of the green rocks that you're sampling relative to the center. So it's known, it's well illustrated in Scott Halley's paper in Economic Geology, for example, that the chlorite chemistry becomes more iron rich as you're in more lower pH environments. So as you're in a sort of chlorite sericite transition, maybe proximal but above a porphyry center, you start to get more iron rich chlorite stabilized in the lower pH environment, as opposed to the deeper propylitic environment where the proximal chlorites are more magnesian. So there's a shift with elevation, which is kind of reflecting pH, I think, in the magnesium ion dominance in the chlorite. So depending on what type of system you're looking at, you will get a different behavior in some of those elements. For the trace elements, like the ones I've shown here, most of the systems we studied show this same sort of behavior for these trace elements. That's what I say, really.
Okay. Yeah, it's 15 past, Jamie. I know you have to leave at some point. Maybe we can wrap up with 1 or 2 questions. What do you think, Jamie?
Yeah, I'm happy to take a few more. I don't have to rush off right away.
Okay.
Yeah. So if we're going to do that, if we're going to ask a few more questions, the next question on the list is from Mike Johansson. So if you're still here, Mike. you can ask your question. I don't think he is here. I'm typing his name in. Okay, in that case, he's asked essentially how does overprinting from epithermal deposits or any type of ore deposits modify propylitic alteration? Or does it?
I mean, that's a great question. So we can do a case study, somewhere like Badajoz, which is relatively simple, fairly homogeneous host rocks, and you get a really nice clean pattern. It is complicated. It's not really shown on these plots, but there is an epithermal, low sulfidation epithermal system of bamboo that sits somewhere in here, and we do see the effect of that in some of the elements. So manganese, lead, zinc are all kind of show a kick in that area. Samples that are proximal to that vein system. So those things do modify the propylitic characteristics. They have their own type of propylitic alteration around them that is actually chemically distinct. So I showed you that with the high sulfidation porphyry example from El Indio. So there are things in the high sulfidation associated propylitic mineral chemistry that distinguish it from porphyry related. So that we are developing techniques where you can distinguish between these different types of propylitic alteration. And obviously, many porphyry districts have these epithermal systems mixed in with where the porphyry centers are. And so discriminating them is important, because if you want to use these targeting methods, that's only going to apply to the porphyry propylitic alteration. It's not going to apply to samples that have an epithermal signature. So discriminating those is important. You can then screen those out and only focus on the porphyry related stuff. And there are ways that you can do that with the chemistry. And then lastly on that, we're also doing, as I mentioned, dating. So you could date the propylitic assemblages using apatite, epidote potentially, and titanite. And that allows you to separate systems that may be significantly different in age. The resolution of that laser ablation dating is not fantastic, but it's good enough to separate things that are, reasonably different in age. If you're talking about things that are just a few million years apart, then you don't have the resolution to do that. But certainly tens to hundreds of millions of years apart, you can separate those using geochronological methods as well. But that's a very good question, because that's the reality of a lot of these sorts of exploration areas.
Oh, that's a good answer. Have you got another question, Marion?
We have a question from Alberto Lobo Guerrero. He is asking what indication have been observed in zeolite, prehnite, or titanite.
Yeah, it's a as you sort of delve deeper into this type of work, you find minerals there that are quite common that just nothing's been done on. So I've seen zeolites quite commonly in porphyry propylitic systems. They tend to occur around the outside. Some of the spectral stuff we did in Badajoz picked up zeolites in samples that are generally fringing around the edge of the propylitic kind of halo. So they're there, but we haven't done any work on zeolite chemistry or what that might tell you. There's plenty of scope to do that kind of work. Titanite we are doing more work on. We've done geochronology on it, and we're starting to do the trace element chemistry of titanite, not only in the propylitic alteration assemblages where you get titanite, but also in the igneous side. So you get titanite as a primary igneous phenocryst phase, particularly in the later stages of evolution of oxidized arc magmas. So we're looking at the titanite record from the igneous perspective, but also what it can tell us about propylitic. So we're doing some work on titanite, but there are the other minerals like prehnite. Yeah, we haven't done anything on prehnite. Abundance, distribution, chemistry. There's plenty of scope to work on those things too.
Sure. Yeah, I guess we can try to wrap up this talk. I have a question here for that. Could you say that there is now sufficient data to start relating gradient to robustness of the system?
You mean how well developed or how well mineralized a system is?
I guess so, or I could rephrase the question is like, how robust is this database nowadays for exploration?
So the what's published is just the tip of the iceberg, really. I mentioned this earlier to you, Marion, but the Green Rocks issue, was the first main set of papers that came out of the Amira project work, the economic geology issue last year. And and there's lots more data that hasn't been published. So there's probably around 40 or 50 case study sites that have been studied around the world with varying amounts of propylitic data collected. L10 is one of the biggest ones, several hundred samples there. So that's why that's a good study site, and that was published in that issue last year. But there are many other study sites that have data. So there's like a lot of knowledge that's not in the public domain yet that sort of gives us confidence that a lot of these patterns are reproducible. In terms of application, so the methods are being used by some of the major exploration companies as part of their exploration portfolio. So Rio Tinto use this a lot, for example. And I think it would be a sort of generally observed thing that if you get a really strong convergence of the sort of distance predictions I'm been showing you, then that is a good sign that there's a strong hydrothermal center there. In some of the brine test study sites where you've got sort of multiple weaker centers all in the same area, it gets very hard to kind of recognize where they are. They're overlapping each other and you don't get a strong signal. But where you have a really well-developed hydrothermal center, it kind of self-organizes itself to have a strong chemical gradient and halo around it over some period of time. So where you get a really strong prediction is generally where there is a really strong hydrothermal center, a really well-developed center. So that's one thing. And then the other thing is that there are some tools that I haven't really talked about today where the chemistry, particularly of some of the pathfinder metals like zinc and manganese, do seem to reflect the amount of metal that's been fluxed through a system. So the halo that you see in those elements in some of the propylitic minerals is generally higher, more elevated, and quite often pushed out to a greater distance where you've had more flux of fluid through the system and where the system is bigger and more mineralized. So there are potentially some fingerprints in the propylitic minerals that even if you're only sampling stuff from quite far away, you can get a sense, some idea of how much mineralization there may be in the core even before you've found it. So there are some fertility kind of endowment, perhaps a better word to use, tools that can help you tell whether it's not just there's probably something there, but potentially how good it is as well.
Great, thanks. Jamie, Kelly, anything else to add, or should we wrap up that here?
Well, there is still a few questions, but I understand that Jamie's time is constrained. So if you're happy to wrap it up here, Jamie, then we're obviously happy to wrap it up.
It's up to you. I mean, I can take a couple more if you want. I can go to past. That's not a problem.
Okay. There was one person who unfortunately left the meeting, but did really want to ask the question. His name's Scott Spurrier, and they asked something about the quite relevant because you talked a lot about titanium, strontium, and they asked, is this trace element geochemistry, titanium, strontium, etc., useful in whole rock analysis, or do you have to use SEM and laser ablation, ICP-MS, specifically on chlorite? So I think it's quite relevant to exploration, I think, this question.
Yeah. So the point is that yes, you do have to use laser ablation, because if you, for example, we did this, and I think it's in the paper here on this slide, Journal of Geochemical Exploration paper. If you plot the whole rock titanium, for example, in these samples, it's completely flat. These are mainly basaltic andesites. The titanium doesn't change in whole rock. So what we're detecting in the chlorite is just the small amount that is partitioning into the chlorite, preferentially as a function of elevated temperature when you get closer to the center. So you're talking about, there's no effect on the whole rock. The titanium is probably not mobile really at all on the whole rock scale across the system. In terms of those mass transfer things, it would show probably no change. So there's no addition of titanium in the core. It's just redistributing itself within the rock between the different minerals as they're crystallizing in the propylitic assemblage, and the chlorite's recording the thermal fingerprint, the thermal imprint of that process as it forms. But with only tens to hundreds of up to about 1,000 ppm, it's not large amounts of titanium that are going into the structure. So you don't see that in whole rock. Maybe in lithium, you would see some depletion in the core, but then if you were sampling those rocks, you'd be basically sitting on top of the porphyry system anyway. So when you get further out in the area where the green rocks can add value over traditional techniques, then you wouldn't see the gradients in lithium or other trace elements in the whole rock. Manganese and zinc you do. So where you see a halo of manganese and zinc enrichment around a porphyry system, which you often see maybe 1.5 kilometers out, as I illustrated in some of those maps earlier on in the talk, that metal dispersion you will see in whole rock, and it maps onto where you see the enrichment of those elements in the chlorite mineral chemistry. But it's much more systematic in the chlorite. So the whole rock can be quite erratic. It's quite nuggety, probably maybe related to sort of being controlled by sort of trace sulfide presence or absence in a broad domain in space. But the chlorite seems to pick it up and substitute it more systematically. So you see the same things, but the chlorite has a more systematic pattern to it in the way it incorporates it than the whole rock does for zinc and manganese specifically.
Awesome. Right, looking through, I think most of the remaining questions have been answered in some way. There is some questions about whether or not you can use this methodology for other mineral deposit types. I think that's an ongoing piece of work, to be fair.
Yeah, and I think that's a good question, and perhaps a good one to end on. I think, particularly chlorite or epidote as well is very widely developed in hydrothermal systems. Almost all hydrothermal systems probably have some chlorite. So it has huge potential probably in any hydrothermal setting. I don't think at the start we were very confident that it would have systematic chemical behavior in terms of trace elements, but it clearly does. And from the work we're now starting to do in epithermal environments, you can certainly see gradients away from epithermal ore deposits, and they have their own chemical flavor, chemical characteristic that allows you to discriminate them. We've done a very little bit on a VMS system, and again there is behavior there. There are systematic patterns, but it's not something we've explored a lot. Orogenic gold deposits, there's a bit of data in the Amira studies of one system which showed again really large scale kind of zonation type patterns in epidote and chlorite around that type of system as well. So I think you will find them. People will find them in many hydrothermal settings. It just requires quite a lot of samples over quite a good grid sampling over quite a large area to recognize them, and a lot of analysis. Yeah.
Brilliant. Well, I think that brings everything to an end. So thanks everyone for attending. I did put a link in the chat for the certificate of attendance. So if you haven't checked that out, scroll back and you'll be able to click on that, fill it out. But yeah, really, thanks very much, Jamie, for attending this talk and giving up your time. Thanks everyone for attending, and I think that wraps it up from me.
Thanks so much for organising it all and all your hard work in putting these together. It's a really great thing. So well done.
Thanks.